In the quiet hours, when the world settles into darkness, a silent hunter takes to the sky. It moves through the air like a ghost, a phantom unseen and unheard. This creature is the owl, a master of the night. For centuries, we have seen it as a symbol of wisdom, mystery, even magic. It appears from nowhere, strikes with impossible speed, vanishes back into the shadows. This perception of magic is not just folklore. It is rooted in a deep, observable truth. Owls seem to defy the very rules of the world we understand. They are nature's illusionists, performing feats that appear to bend the laws of physics. But what if this magic is not magic at all? What if it is a form of physics so advanced, so perfectly refined, that it looks like sorcery to our eyes? The owl's silent flight is not an enchantment. It is a masterpiece of aerodynamics. Its uncanny ability to pinpoint prey in total darkness is not a sixth sense. It is a triumph of acoustic engineering. Every seemingly supernatural feat is the result of millions of years of evolution, sculpting biology into a perfect engine of stealth and precision. The owl has not broken the laws of physics. It has mastered them in ways we are only just beginning to comprehend. Tonight, we will pull back the curtain on this natural magician. We will explore how the owl has harnessed the fundamental forces of our universe to become the ultimate nocturnal predator. We will go beyond the familiar image of the wise bird and delve into a world of specialized feathers, asymmetrical ears, biomechanical wonders. This is not a story about myth or legend. It is a story about science, about the hidden physical principles that govern the life of this extraordinary bird. We will see that the truth behind the owl's abilities is far more fascinating than any magic trick. The stakes for the owl are incredibly high. In the unforgiving darkness, a single mistake means the difference between a meal and starvation. A single misplaced sound can alert its prey, causing a vital opportunity to be lost forever. Every hunt is a delicate balance of energy, sound, movement. To survive, the owl cannot afford any errors. This pressure has driven the evolution of a set of physical adaptations that are unparalleled in the animal kingdom. We will witness how this constant challenge has shaped a creature that embodies the pinnacle of predatory efficiency, turning its very body into a finely tuned scientific instrument. The owl possesses a toolkit of strange and wonderful abilities, each one a puzzle waiting to be solved. The most famous of these is its power of silent flight. Think of any other bird of this size, a pigeon, a hawk perhaps. You can hear the powerful beat of their wings as they pass overhead. The air itself seems to tear and rush around them. Yet an owl can glide inches above your head and you would not hear a thing. It is a biological stealth bomber. This silence is not an accident. It is a carefully engineered feature, a secret weapon that makes the owl one of the world's most effective ambush predators. This silence is just the beginning of the owl's mysteries. Its hearing is just as remarkable. Many owls can hunt in complete and total darkness, relying on sound alone. They can hear the faintest rustle of a mouse under a thick blanket of snow and pinpoint its location with astonishing accuracy. How is this possible? The owl's face is not just a face. It is a sophisticated satellite dish designed to collect and focus sound. Its ears are not placed symmetrically like ours. This strange, lopsided arrangement is the key to creating a three-dimensional map of the soundscape, allowing the owl to see with its hearing. Beyond flight and hearing lies a world of unseen biomechanics. Consider the strike itself. From a silent perch, an owl can launch an attack with explosive speed and force, yet its movements remain fluid and controlled. Its head can swivel an incredible 270 degrees, allowing it to scan its environment without moving its body and making a sound. Its talons are weapons of immense power, capable of crushing prey with a grip that is both swift and final. These are not simple actions. They are complex biomechanical events involving specialized muscles, elastic tendons, and unique skeletal structures that we will investigate. These abilities, silent flight, acoustic targeting, and incredible biomechanics, are the secrets we promise to reveal. They are adaptations that have been hidden in plain sight for millennia. We often admire the owl for its beauty and its mysterious aura, but we rarely ask how it achieves its incredible feats. Tonight, we will ask those questions. We will uncover the physics behind the phantom, the mathematics behind the hunt, and the engineering behind the anatomy. We are going to look at the owl not just as an animal, but as a living, breathing marvel of natural design. To understand the owl's magic, we must become scientific detectives. Our investigation will combine several fields of study to build a complete picture of this incredible hunter. We will start with the fundamental principles of physics. Mathematics. These are the universal languages that describe how things move, how forces interact, how energy flows. We will use these tools not as dry, complicated subjects, but as keys to unlock the owl's secrets. Simple equations will help us understand the profound effects of the owl's unique design. Aerodynamics, acoustics. Our journey will also take us back in time, through a rich collection of archival evidence. We will look at the pioneering work of scientists who first began to unravel these mysteries. We will examine incredible slow-motion footage that breaks down the owl's flight, wing beat by wing beat, revealing the subtle movements that cancel out sound. Through powerful microscopes, we will explore the intricate, velvet-like structure of a single owl feather. These historical documents and scientific recordings provide the crucial evidence, the fingerprints left behind by evolution, that show us exactly how the owl's adaptations work at the smallest scales. Of course, a story like this must be seen to be believed. We will use vivid, modern visuals to bring the physics to life. Computer-generated graphics will illustrate the flow of air over an owl's wing, comparing it to that of a louder bird. Animations will show how sound waves travel to the owl's asymmetrical ears, allowing its brain to calculate the precise location of its prey. We will use thermal imaging to see the world from an owl's perspective and force plate data to measure the power of its silent strike. This combination of visuals will make the unseen forces visible, creating an immersive and exciting experience. This documentary is our plan, our roadmap into the hidden world of the owl. We will unite physics, biology, and history to deconstruct the owl's hunting magic. From the leading edge of its feathers to the elastic power of its talons, we will explain how every part of the owl is a solution to a physical problem. We will show you how nature, through the relentless process of natural selection, has produced a creature that can manipulate sound and air with a level of sophistication that human engineers can only dream of. Prepare to see the owl as you have never seen it before. Table of Contents, Part 2, Act 1, Flight and Feather Physics. Section 1, The Basic Principles of Flight. Section 2, The Owl's Unique Wing Shape. Section 3, The First Secret, The Serrated Leading Edge. Section 4, The Second Secret, The Velvety Upper Surface. Section 5, The Third Secret, The Fringed Trailing Edge. Section 6, The Mathematics of Silence. Section 7, The Trade-off, Stealth over Speed. To understand how an owl achieves its silent flight, we must first understand how any bird flies at all. Flight is a constant battle against gravity, a struggle fought in the invisible medium of the air. It all begins with two fundamental forces. Lift is the upward force that keeps a bird in the air. Drag is the resistance that tries to slow it down. For a bird to fly, the lift generated by its wings must be greater than its own weight. It is a delicate and energetic balancing act, perfected over millions of years of evolution. The secret to generating lift lies in the shape of the wing, known as an aerofoil. A bird's wing is curved on top and flatter on the bottom. As the wing moves through the air flowing over the curved top surface must travel a longer distance than the air underneath. To meet up at the back at the same time, the air on top must move faster. Bernoulli's principle says faster moving air has lower pressure. Higher pressure below the wing, lower pressure above creates a net upward force, lift. However, it's not perfectly efficient. Pushing through the air creates drag, opposing forward motion. Much of that drag comes from turbulence. Air can become chaotic and swirly, especially at the wingtips and the trailing edge. This turbulence creates noise, the familiar whooshing of a pigeon or a goose. For most birds, that's an unavoidable byproduct of powerful flight. It's the audible signature of the immense effort to stay airborne. Enter the Reynolds number, a simple number that helps predict how air will flow around an object. For large, fast flyers like an aeroplane, Reynolds is very high and flow is often turbulent. For tiny, slow insects, it's low and the air flows smoothly. An owl sits in the middle, relatively large, but flying very slowly. That mix creates a unique aerodynamic challenge, and its solution is what makes owls special. An owl's wing is not like that of a falcon built for speed, or a vulture built for soaring on high-altitude thermals. Falcon built for speed, vulture built for soaring. The owl's wing is a specialist tool designed for a very specific purpose. Slow, silent, controlled flight close to the ground. When you look at an owl's wing, the first thing you notice is its sheer size relative to its body. Broad, long wings with a very large surface area. This large area is critical. It allows the owl to generate a significant amount of lift, even when flying at incredibly slow speeds. This large wing area allows the owl to fly with a very low wing loading. Wing loading is simply the bird's body weight divided by the area of its wings. A fighter jet has a high wing loading, requiring immense speed to stay in the air. A glider, on the other hand, has a very low wing loading, allowing it to drift gracefully on the slightest breeze. The owl is the glider of the predatory world. This low wing loading means it can stay aloft with minimal effort. It can float, hover, and maneuver with a slow, deliberate grace that other birds of its size cannot hope to match. Furthermore, the flapping motion itself is different. Watch a pigeon take off, and you see rapid, powerful, and noisy wing beats. They are desperately trying to generate enough lift to get their heavy bodies into the air. An owl's wing beat is the complete opposite: slow, deep, methodical. Each downstroke is a long, careful push against the air. The upstroke is equally unhurried. This slow flapping cycle is key to its silence. Fast movements create high-frequency, audible noise. By slowing everything down, the owl shifts the sound of its flight to a much lower frequency, often below the range of hearing for its primary prey. This combination of a large wing surface and a slow flapping speed creates an exceptionally stable and steady form of lift. There are no sudden bursts of power or frantic movements. The owl's flight is smooth and continuous, almost like it is swimming through the air. This stability is vital for a hunter that relies on listening. A noisy, turbulent flight would be like trying to listen for a whisper during a rock concert. The owl's own flight would deafen it to the subtle sounds of its prey. The very shape and motion of its wings are the first step in creating a platform of perfect silence. Now we move from the overall shape of the wing to its microscopic details. Here we find the owl's three great secrets to silence, adaptations so refined they seem almost engineered. The first of these secrets is found on the very front of the wing, the leading edge. If you were to run your finger along the leading edge of a typical bird's feather, it would feel smooth and firm. But on an owl, the primary flight feathers have a completely different structure. They possess a stiff, comb-like fringe, a series of tiny hooked serrations pointing forward into the oncoming air. These serrations are not a random feature. They are a sophisticated aerodynamic device. As the wing moves forward, this comb-like edge breaks up the flow of air. Instead of hitting a single solid surface and creating a large pressure wave, which generates sound, the air is channeled through these tiny serrations. This process transforms a single, large, noisy pocket of turbulence into many smaller, quieter ones. These smaller swirls of air are called microturbulences. They still exist, but their energy is dissipated much more quietly and at a higher frequency that is less likely to be detected. This is a principle that human engineers have recently started to copy. You can see similar serrated edges on the blades of wind turbines and even on the wings of some advanced aircraft. The goal is the same: to reduce noise by carefully controlling how air flows over a surface. But the owl has been using this technology for millions of years. It effectively smooths the passage of air over the most critical part of the aerofoil, right where the initial impact with the air occurs. This first point of contact is a major source of noise for other birds, but the owl has found a way to muffle it. The effect of these serrations is profound. Scientific studies using sensitive microphones in wind tunnels have shown that this leading-edge comb can reduce flight noise by a significant margin, especially in the sound frequencies that small mammals like mice and voles are most sensitive to. It is the first of a three-part system for silencing its wings. It does not eliminate noise entirely, but it tackles the problem at its source, breaking down the sound-producing turbulence before it even has a chance to fully form. This is the first layer of the owl's cloak of invisibility. After the air passes over the serrated leading edge, it flows across the top surface of the wing. On a typical bird, this surface is relatively smooth and rigid, designed for maximum aerodynamic efficiency. But the owl's wing holds another secret here. The feathers on the upper surface of its wing have a rich, velvety texture. Under a microscope, this surface reveals itself to be a dense forest of tiny, hair-like projections. Esim close-up showing dense, forest-like barbules. This downy covering is not for warmth. It is the owl's second secret to achieving silence, and it works in a completely different way from the leading-edge comb. This velvety pile serves as a sound-absorbing layer. Any noise that was generated at the leading edge, or any noise created by air flowing over the wing's surface, is not reflected away. Instead, it gets trapped in this complex, three-dimensional forest of fibers. The sound waves bounce around within the velvet, their energy dissipating as heat, effectively muffling them before they can escape and travel down to the ground. It is the biological equivalent of the acoustic foam panels you might see in a recording studio, designed to stop echoes and absorb unwanted sound. This adaptation is particularly effective at absorbing the high-frequency sounds that are most likely to startle prey. Snaps, crackles, whooshes. Small rodents have hearing that is acutely tuned to those sounds. The owl's velvety wing surface acts like a sponge for these specific frequencies, soaking them up and rendering the owl acoustically invisible to its next meal. The air might still be turbulent at a microscopic level, but the noise of that turbulence is trapped and silenced by this remarkable feather structure before it can betray the owl's presence. This feature is a perfect example of evolution finding a multi-purpose solution. This soft surface does more than just absorb sound. It also helps to smooth the flow of air across the wing, further reducing the formation of sound-generating turbulence. It works in perfect harmony with the leading-edge serrations. The comb breaks down large pockets of turbulence, and the velvet surface then absorbs the noise from the smaller turbulences that remain. It is a two-stage silencing system, a 1-2 punch against the physics of sound production, ensuring that the air passes over the wing in near-perfect silence. The journey of air across the owl's wing is not over yet. After being broken up by the leading-edge comb, quieted by the velvety upper surface, the air reaches the back of the wing, the trailing edge. In most birds, this edge is sharp and firm. As the air from the top and bottom surfaces of the wing meets here, it can create vortices and shed turbulence. This is the sound of the wake, the disturbed air a bird leaves behind. The owl, however, has one final trick to play. Its third and perhaps most elegant secret to silence. The feathers at the trailing edge of an owl's wing are not firm and solid. Instead, they are soft, flexible, and porous. They end in a delicate, wispy fringe. This fringe acts like a silencer on a firearm, but for air. As the air flows from the upper and lower surfaces of the wing recombine, this soft edge allows them to mix together gradually and gently. There is no sharp, abrupt meeting point that would generate noise. The air streams merge smoothly through the porous fringe, dramatically reducing turbulence in the wake and silencing the final potential source of sound from the wing. This fringed edge is critical for eliminating trailing edge noise, often the dominant source of sound at the owl's flight speed. By smoothing out the wake, the owl ensures it leaves behind a silent trail. It is not enough to be quiet as you approach. You must also be quiet as you pass over. Even a prey animal directly underneath will not hear wings that just passed inches above its head. It completes the system of silence, addressing the beginning, middle, and end of the airflow over the wing. Together, these three adaptations, the serrated leading edge, the velvety upper surface, and the fringed trailing edge, form a sophisticated, integrated system. They are interlocking solutions to the single problem of noise. Their combined effect is a reduction in noise that is almost total. Human engineers are still studying and trying to replicate this aerodynamic refinement. The owl's wing is not just a tool for flight. It is a masterpiece of acoustic stealth, you know. We can observe the owl's silence and marvel at its adaptations, but to truly appreciate their power, we need to quantify it. We need to use the language of mathematics and physics. Scientists have done just this, placing owls in special anechoic chambers, rooms designed to be completely silent, and recording their flight with highly sensitive microphones. The results are astonishing. When they compare the sound signature of an owl to that of a pigeon, or a hawk of similar size, the difference is not small. It is monumental. The sound produced by an owl in flight is often measured to be more than 10 decibels lower than that of other birds at similar speeds. The decibel scale is logarithmic. A 10 decibel reduction means the sound intensity is actually 10 times lower. In some of the key frequencies used by prey, the reduction can be even greater. For a mouse hiding in the grass, this is the difference between hearing a clear and terrifying whoosh and hearing absolutely nothing at all. The owl operates below the audible threshold of its dinner. We can express this benefit using a simple equation related to sound intensity. The intensity of sound decreases with the square of the distance from the source. This is the inverse square law. It means that a loud bird, like a hawk, has to be very far away for its sound to fade. But because the owl's initial sound intensity is so incredibly low to begin with, it becomes effectively inaudible at a very short distance. An owl can be just a few feet away, well within striking range, and still be completely silent to its target. This mathematical advantage is the core of its hunting strategy. These numbers transform our understanding of the owl. What seems like magic is, in fact, a quantifiable physical advantage. The serrations, the velvet, the fringe are not just interesting biological quirks. They are precision instruments that manipulate the laws of acoustics. By reducing the source noise by a factor of 10 or more, the owl dramatically shrinks the detection radius of its prey. It creates a stealth bubble around itself, a zone of silence within which it can hunt with near-perfect impunity. It is a victory won not with brute force, but with the subtle and undeniable logic of physics. This incredible ability for silent flight does not come for free. In nature, every adaptation involves a trade-off. The features that make an owl's wing so quiet also make it less efficient for other types of flight. The soft, porous surfaces of the feathers, brilliant at absorbing sound and smoothing airflow, are not as good at generating raw lift and power as the stiff, rigid feathers of a falcon, a swift. The owl has traded pure aerodynamic performance for acoustic stealth. This trade-off is most evident in its speed. Owls are not fast flyers. A barn owl's typical hunting speed is slow, often less than 10 miles per hour. A peregrine falcon, by contrast, can dive at speeds exceeding 200 miles per hour. The falcon is an aerial missile, built for high-speed pursuit in open daylight. The owl is a stealth aircraft, built for slow, silent ambush in the dead of night. Its wing is not designed to race. It is designed to loiter, to drift silently over a field, listening and waiting for the perfect moment to strike. This compromise also affects its maneuverability in some ways. While an owl is exceptionally agile at slow speeds, able to make tight turns and hover, its wings do not have the rigidity needed for the high-G maneuvers of a dynamic chase. The soft trailing edge that is so crucial for silence would likely flutter and lose effectiveness at high speeds. The entire flight apparatus is finely tuned for one specific ecological niche: the low and slow nocturnal ambush. It has sacrificed the ability to be a jack of all trades to become the undisputed master of one. This trade-off perfectly illustrates the pressures of evolution. There is no single best wing design, only the best wing for a particular lifestyle. For the owl, the supreme advantage is to be unheard. The cost of a slight reduction in speed or power is a small price to pay for the ability to approach its prey without detection. This choice, made over millions of years, has shaped the owl into the ultimate silent hunter. It is a creature that has embraced a specialized strategy, and in doing so, it has harnessed the physics of feathers to become the undisputed magician of the night sky.